Hello friends, we are going to learn the intermediate code. You know, the intermediate code is a machine independent code. After the high level code, we have the intermediate code. Both codes are machine independent codes. Now we have assembly code as well as machine code. They are machine dependent code, but intermediate code is somewhat very special, which is going to be the intermediate to the high level and the machine code. So which stays the intermediate to both of them, so that it will be very easy to convert high level to intermediate and intermediate to machine code. That is why we require this intermediate code support, and somebody has to generate this code so that it will become so easy to generate assembly code. Okay, before learning about intermediate code, so what we have learned so far: lexical analysis, syntax, SDTs. Now we are going to learn intermediate code. Then we will see code optimization at the end. What is the intermediate code? Intermediate code is generated by intermediate code generator. So ICG, which is nothing but intermediate code generator. For this you will give high level code, let's say C code you are going to give, but which is analyzed code, where lexically, syntactically, semantically should be correct. So this high level code given to ICG, and what ICG produces? Intermediate code. Now the question is, what is intermediate code, right? So intermediate code generated by intermediate code generator. So this is generator, intermediate code generator. Now we have to look at the importance of intermediate code, but before that, what is intermediate code? To understand this intermediate code, you should know various representations of intermediate code. When I write high level code, let's say x is equal to a plus b star c, you know, it looks very big, right? This is high level code, and when you give this to intermediate code generator ICG, what it does, it produces some intermediate code. So what is the importance of this intermediate code and how it looks like? So this high level code, when you convert it, that should become so easy to convert into assembly code and then machine level code. So if you want to convert this code into machine code, you know, machine code, let's say assembly code first. In the assembly code, at a time you can do only one operation, like either you can do multiplication, or you can do addition, or you can do a move. That move is different. So look at only addition and multiplication. You cannot do addition and multiplication in a single instruction at assembly level. So this intermediate code is going to help you. It's going to be very near to assembly code and looks like high level code. So that's a very specialty of intermediate code. This is a machine independent, no doubt. Even this high level code is also machine independent. But what is the advantage of having intermediate code? Will become so easy to convert into assembly code. That is the reason we prefer intermediate code here. So how that looks like? There are many representations. One representation I am going to tell you. Let's say T1 is equal to, is a one representation. Multiplication will be done in one instruction. Another instruction will be done in addition. That addition, a plus the b star c already stored in T1. So a plus T1. Really you want to move to x. Okay, T2 you can move to x. See, except assignment, if you look at the RHS, you are doing multiplication, addition. So each time you do single operation. That makes a sense in assembly code. When you convert to the assembly code, for this you can use multiplication instruction MUL. For this you can use add ADD. You can use a move instruction for the third one. So it becomes so easy. But if I ask what is the equivalent assembly code for this, oh, you need to think which one to perform. So you are having a lot of things to do to convert into assembly code. So this intermediate code generator is going to help us to convert this into some intermediate form, and that will become so easy to convert to assembly level. So that's the main advantage of intermediate code, and you can optimize further. So this kind of code can be optimized with the help of code optimizers. So that is another advantage of this intermediate code. And today you can use this intermediate code for many systems, so that you can make a standard intermediate code where every machine can understand, so that they can take the intermediate code and they can convert into assembly code very easily. Okay, now the question is, the intermediate code also helps for various programming languages like C, C++. There are various programming languages, but all of them intermediate code you can make unique, so that the system do not worry about are you writing C or C++. Once you give intermediate code, then the machine understands what to do. But before that, you need to use the compiler properly to analyze and convert into intermediate code. So understand, whether it is C or C++, till intermediate code only different, but after that the C intermediate code and C++ intermediate code, you may not see the difference, because you can make a standardized intermediate code. Fine. So I hope you have some purpose why we convert into intermediate code. Now the question is, what are the representations? What are the representations you have? There are various representations. The very famous one is the 3-address code. That's why I have shown that code is 3-address code. This is very famous, and for the exam point of view which we require. Another one, static single assignment. Which is also 3-address code, but restricted somehow. The first one you can call it as TAC or 3AC. The another one is SSA, static single assignment code. Third one, you can also write postfix. Fourth one, you can draw a graph if you really want it, syntax tree. You can also draw variation of syntax tree is directed acyclic graph. You can also call it as DAG, D-A-G, DAG. And you also have control flow graph. Anyhow, that we will study slowly in code optimization, but you also have, remember that control flow graph can be called as CFG. So we are going to look at the first 5, and sixth one will study in code optimization there itself. Now come to the point, this representations are 2 types from outside. These are linear, because you write statement by statement, but here you draw the graph, so we call it as a non-linear representations, some pictorial or graph representations. Okay. Now what is this 3-address code, how it looks like, and we are going to learn each one here. Let's start with 3-address code. And if you want to produce intermediate code, your system or your translator has to understand any of this and produces according to your requirement. So some systems, you may take as 3-address code as intermediate code as 3-address code, or intermediate code is maybe SSA code, or intermediate code maybe postfix, maybe graphs, syntax tree, direct acyclic graph, or control flow graph. Okay. First one, 3-address code. So what is this 3-address code? Sorry. First one we'll see postfix code. Did I miss the sequence? Yes. First one we'll see the postfix code. What is a postfix code? Suppose you have an expression a plus b star c. Before this, let me help you. When you have, let's say, x plus y, what is the equivalent postfix code? You write x y plus. So this is infix, this is postfix, and this one is postfix. When you have x multiply with y, you write x y multiplication. If you have x minus y, you will write x y minus, right? So similarly, you have a lot of expressions based on the operators available in the language. Okay, you may use many things like this. Now come to this expression, I want to convert into the postfix form, so that will be one of the intermediate codes. Now assume this is a high level expression. Now how do you write the postfix code? And who is having more precedence? Multiplication. So we'll write BC star. And now this will become one operand after performing the multiplication. Now a plus some result. What happens? A and some result plus we will send out. That's it. So this is called as postfix code. So you may produce this postfix code as intermediate code from the intermediate code generator. so that this can be used for the other phases, like code generator can take this one and produces equivalent assembly code. How it produces? Very simple. See, it's trying to remember like this: A, then B, C. First operation comes like multiplication, so the last two operands will be taken as the operand 1 and operand 2 and performs multiplication. So it can easily understand, okay, multiplication should be done first, then addition. Okay, so this is one of the advantage of having the intermediate code. Now let's move to the next one, that is 3-address code. What is 3-address code? The name itself says that a code which has maximum 3 addresses. You are going to deal with maximum 3 addresses. Why is that? If you look at the standard assembly codes, the most of the assembly codes, they follow the 3 addresses. Like if you are writing, let's say, add A comma B, then you take 2 inputs A and B and you will send to some register, let's say A, as the target. So you are dealing with 3 addresses where the A plus B will be stored in A. So something like you have to move to A, or sometimes you may write add A comma B comma C. Maybe you will add B and C and then you will put in A. That's also fine, but maximum you will deal with the 3 addresses in most of the standard assembly codes. Now here, what do you mean by 3-address code? You will be dealing with variables here, because as you do not deal with addresses directly, so we use the variables to represent address. So if I am using at most 3 addresses, it means I am dealing with if I am representing with 3 variables, it means I am dealing with 3 addresses. Okay. What is the example? Suppose I have A plus B star C. Then how do you write it? The B star C, we will put in some variable, let's say T1, and we will add with A. A plus T1 will store in, let's say, T2. So this is called as 3-address code. If you look at maximum address that you are dealing, maximum variables that you are dealing is 3 here: C, B, T1, T1, A, T2. Okay, maximum. This is called as 3-address code. Okay, for that you need to practice lot. Do you really need it this way to convert? No, you can also write your own 3-address code. So I can also write some other way to save my space. B star C, I can store in B if really B is not needed in the future, or you can store in C, you can assign to C if C is not needed in the future. So here I have only this instruction or statement, that is why I know that B and C are not there next. So I can store there. Now A plus B, I can store in A or B or C, you decide, you can store in any. So let me store in A, that's fine. The result is there in A. So what is the advantage of writing this kind of 3-address code? You just need 3 addresses for representing whole expression A, B, C. 3 variables you require here. Here how many? A, B, C, 3 given, and T1, T2 you have taken additionally 2 variables. Totally here you need 5 variables. Here you require 3 variables. Of course, which 3 variables, how to use them, that is given completely, but how to use them you decide. Fine. So this is called as best 3-address code, optimized version of 3-address code, but here you have it's not optimized one, it's wasting a lot of space to do the same job. Okay, we prefer always this kind of code. In the exam, if they ask how many variables, always find minimum number of variables. Don't answer blindly 5, 4 like this. You need to find the best answer for this. Okay, that's about 3-address code. Next, SSA code, static single assignment. What is it? Static single assignment. Static single assignment. Basically this is also 3-address code. It is 3-address code only, but where is the change? Where is the change? In 3-address code, suppose I am writing I am doing A multiply with B. You can store in A, but here you can't, because static single assignment means every variable should have the single meaning. Every variable should have the single assignment. Every variable should have the single definition. Now here A is already have a meaning. Now you are changing the meaning, you are defining A again. That means A value may change. So this is nothing but it's not SSA code. This is called as not SSA. You can't change the meaning of A in the code in SSA code. So every variable should have the single assignment. It is 3-address code. Every address or every variable that we use, every variable has single assignment, means single definition, single meaning, right? Fixed, static, single assignment, static, fixed. You can't change the meaning of or value of A, something like that. Now that's called as SSA code. To understand how do you rewrite this code to make SSA code, you can put in some new variable always, T1, right? T1 is not there in the code, so I can use T1. Now this is called as SSA code, right? Every variable that you have used has a single assignment. That's A has a single meaning, B has a single meaning, and T1 now you got a new meaning because you defined just now. Okay, so you need to practice again to write SSA code. We'll see some examples. I hope you got a clarity. This is 3-address code, no doubt. There is no restriction how to use the variable, how many times you define, no restriction in 3-address code. But in SSA code, every variable should have the single assignment. That means single definition. It means single meaning. Next, syntax tree, and how this is different from the previous 3 notations. In previous 3 we are writing the statements, but here we draw a graph. What is syntax tree? Suppose I have A plus B star. Okay, let me take a very different example, A plus B. So how do you draw a syntax tree? How do you draw a syntax tree? Very simple. You have A plus B, A plus B. So here the intermediate node we always use operator, leaf nodes we use as operands. So always remember, if you have an expression something like this, you make a tree plus A, B, and these are leaf nodes. This is non-leaf node, that's maybe intermediate node or maybe root, depends on the expression. Now A plus B is the LHS of multiplication and A plus B is RHS of multiplication. So LHS, left operand and right operand, left operand, right operand, and the star left operand is a result of A plus B, so we'll connect here, and right operand also result of this one will connect. So to make a difference between leaf and non-leaf, maybe non-leaf you can put a circle but not compulsory, that's fine. So all the circles we represented here with the operators, and all non-circles are leaf nodes, they are operands. So this is called as syntax tree, or you can say expression tree, as you are drawing a tree for expression, right? So it is syntax tree. So every leaf is, what is the statement here? Every leaf is operand, every non-leaf is operator. Non-leaf is nothing but intermediate node or sometimes a root, here is operator. This is called as syntax tree. What is the problem with the syntax tree here? A plus B already is there, but still you are drawing again. So you are wasting a lot of nodes here to edges also there here, nodes and edges. You are unnecessarily wasting the unnecessarily you are using a lot of space to represent same thing again. So to save the space, to avoid the calculations again and again, see A plus B already calculated once, again you are calculating, right? So now to avoid such things, you can approach directed acyclic graph. So next representation is directed acyclic graph. Okay, it's basically if you have any sub-expressions, common sub-expressions, they can be eliminated. It eliminates common sub-expressions. So you have seen an example just now, that is a plus b multiply with a plus b. Okay. Now when you draw a syntax tree, you did not worry about how many nodes and edges. You drawn simply like AB plus another AB, left and right should be careful, and star. You drawn the syntax tree simply like this. Now you want to draw a DAG, how it looks like. Now you can also call it as DAG. It is acyclic graph, means there are no cycles in the graph. Now I am going to draw a graph. You have this one, right? A plus B. I am just writing here plus A, B. Now you have left operand, right operand. So I am just drawing, I just take, A left and B right operand. And let me put the circle is not compulsory. Now already at this place you have the calculation of A plus B, because this can be represented as an address while execution of this code. Now here already result of A plus B is there. Now the same result you can also use here for the right operand of the star. So star, what I do is left operand also I take the same A plus B, right operand also I take A plus B. Now look at how many edges you have. 1, 2, 3, 4. How many nodes you have? 1, 2, 3, 4. So this one just need 4 nodes and 4 edges now. But here if you look at how many nodes we have, 1, 2, 3, 4, 5, 6, 7. Here 7 nodes we have, including leaf nodes, and edges 1, 2, 3, 4, 5, 6. Here you have 6 edges. So who is having a more space? Syntax tree. Who is having less space here? The directed acyclic graph. So always use the directed acyclic graph when you want to save the space and you want to reduce the calculations of the expressions. No need to calculate the expressions again and again. If they are repeated, like A plus B is repeated twice, you can just calculate once and you can reuse the same calculation in other sub expressions. Okay, this is the advantage of DAG. Okay, let's practice. Now you have seen except control flow graph, you have seen almost all intermediate representations. Now the first one, construct a DAG for the following expression. Oh, see this, doesn't matter how do they give, you should have the knowledge of the properties of operators so that you can convert this into the simplest one. Find the minimum number of nodes and edges in the DAG. See, you have A plus A plus A plus B, A plus B plus B. Some expression we have. Right now, there is no rule you need to convert in this way only, right? You just think the best way that gives you the less number of nodes and edges. So what I am going to do here, A plus B plus A plus B. Now you can move this A to that side, or you can move B to this side. Anyhow, you can convert this into A plus B and you can make somehow this one. What is the advantage of doing this? There might be other ways to do, but as you know, you are going to have the subtree with only 2 operands and 1 operator maximum. So this is the best way to do. This is the best way to do. Now once you calculate A plus B, I can use the 3 times. But if you do only 2 times, the A and B you need to add separately again. So total 4 calculations you may need. Suppose anybody thinks like A plus B, 2 additions done, and 3rd addition, 4th addition, 5th addition, total 5 additions. Now look at 1 done at a time, 2nd, 3rd, total 3 additions are enough. So with 3 operations I can close this rather than having 5 operations, doing the add 5 times. Okay, now advantages. Now let's look at how many nodes and edges you take for drawing the DAG for this. A plus B. A and B plus. So we have arrows not required, just for not having cycle, just I am putting up arrow, but you can also put down arrow if you want it. A plus B, done. Now either you can do this one or this one, anyhow it will not change, so I will do this first. So A plus B I am doing adding, right? So plus left operand is same, right operand is same, left operand is same, right operand is same, only one edge it is. So A plus B, done. Now another plus, but left is the result of this one, so this one, but right is only A plus B, so here already there you can take. Now this is the best one, where you have how many nodes? 1 2 3 4 5 nodes. How many? If you can show me with less number of nodes and less number of edges, yours is better than me, but this is the best DAG. And how many edges? 1 2 3 4 5 6 edges. Okay, now you may ask, sir, you are not doing the assignment. Not required. This node is already having the result that represent X. Basically these are addresses, right? Now once you store here, now some address will be there that you can consider as the X. Okay, so do not worry about the assignment. You worry about the operations other than the assignment, because assignment will be the part of the instruction all the time. If you look at assembly instruction, what happens when you do add R1 comma R2? Did you mention assignment? But it happens, right? R1 plus R2, the assignment happens to someone like R1, that you did not mention move here, but after doing the addition it must be stored in some register. If you assume R1, then it will store in R1. Okay, so this is first question, right? Next, now you need to find the minimum number of variables required to represent equivalent 3 address code. Okay, after the DAG, in the DAG we found the number of nodes and edges. Here we will compute number of variables. So how many less number of variables that you can take to perform the same logic? As I told, you need to do some commutative operations. See, any addition is commutative, so you can shift either B to here or A to there. So when you shift it, A plus B, A plus B, A plus B. So this will be the expression. Always remember, the LHS is only one expression, right? Only one assignment statement, so no need to worry about X now. Okay, if you want you can write it, but later on you can ignore it. Now once you bring it like what you did in DAG, similarly you just store somewhere. When you compute A plus B, I am just doing it, A plus B, I am computing. Where do you want to store? A, B or new variable? Here what I am trying to say, once I compute this, now this is done, this is done. Do you have anywhere else doing minus A or multiply with B somewhere else? Do you have any A or B in the future? No. Once you compute this, these two are computed. Means A and B are useless after this computation. So I can restore into A. Then what happens? A plus A you have to do. So what I am going to do? The A plus A. So I am going to compute like this is stored in A. So this will be also stored in A, and this will be also stored in A. Now what I do is A plus A I am going to do, but don't store in A now. Why? If you store in A, this value will change. So you have to store somewhere, let's say B. B is not used right in the future, so I can store in B. Why I am not storing A? Because I need this result A plus B in the future. If you store in A, I will lose this A plus B. Okay, I should not lose. Now B plus A now. B plus A. At this point of time, A and B will be free, because in future there is nothing to compute, and X you do not require additionally, so you are going to store either in A or B. So together B plus A, when you compute, you can store in either A or B. I am just storing in A, but you can also store in B. Now look at the same computation I did with the same A and B, just two variables, but given that 3 addresses, but I did with only 2 addresses. So here 2 variables sufficient total. I have not taken even single additional temporary variables, right? So minimum number of variables required, just 2 for performing the same logic. This is called as best 3 address code or optimized 3 address code. optimized 3 address code. Okay, the next question, you remember this? We will directly do it in the next slide. Remember this? And now we have to do in SSA code. Same question, but find the minimum number of variables in SSA code. Right, you have the same expression too. We have the best technique, like either they give expression or any 3 address code, doesn't matter. For that, you find the best 3 address code. If you can find the best 3 address code for it, that optimized 3 address code, it will be so easy to write. Easy to write the SSA code. What is SSA code? If this best 3 ASC has, let's say, 10 instructions, then 10 additional variables required. That's it. 10 additional variables. If best 3 address code, let's say with n variables, we have, let's say, n variables, and let's say k instructions, k statements, then what happens in SSA code? The best SSA code will have statements will not change, k statements, but number of variables will become n plus k variables. Why? That we will be seeing. And same number of statements will not change. You are reusing the variables previously, now you will create the new variable. So this is how you do it. So to understand this logic, let me explain here. How did you do 3 address code for this? You have written a plus b. So a plus b, and this a you can move to that side. And you have computed a plus b first. So I am writing 3 address code for this, best 3 address code. How did I write? A plus b. I can store in a or b. So let me store in a. This is stored in a now. Now a plus a, you can't store in a, so you have stored in b. Now b plus a, you have stored in, let's say, either a or b, fine. So I have stored in a. This is best 3 address code, but there are many best 3 address codes with 2 variables. This is the best 3 address code what we have here. Okay, if some 3 address code is given, you should write the best 3 address code always. Now how to write SSA code? What is SSA code? What is SSA code? Every variable should have this single assignment, fixed assignment. See, outside a and b have a meaning. You are writing into a means you are giving the second assignment to a. That's not allowed in SSA code. What we do is simply renaming the variables. What I do is a plus b. Now this instead of a will do a1. So this a is dependent here, and also dependent here also, correct? 3 places. So you should know that this is the a1 appeared 3 times, otherwise you may lose that variable. Next, a1 plus a1, actually it is a plus a, but we renamed a1 plus a1, we will store in b, but we don't store in b because b already has a meaning, so we will put b1 here. When you put b1 here, this b is dependent here, so we are going to copy paste b1 here, because you may lose that variable connection because you don't know how long this b is used. Okay, now b1 plus a1 we will store not in a, not in a1, now we will store in a2, but in future there is no a2, and this is the final answer. What did you observe? I have the 3 statements, I got the 3 additional variables. That's why I did here k extra variables you get. Here you have 2 variables only, 2 variables in 3 address code. Best optimized version of 3 address code. But how many variables? Already 2 variables that will be there, but 3 statements will create 3 new variables. So 2 plus 3, we got 5 variables. If you can understand this concept, then most of the questions in GATE you can do easily. Okay, so this is the best way to write SSA code. Always write the best 3 address code. Now no need to do this, just go there. Okay, I have 3 statements, 2 variables, so 3 plus 2, 5 you will get. Okay, so this is, you can save this time to write this code. You no need to write, because from here only you can compute the 5 using this formula n plus k, where n is the number of variables in the best 3 address code, and k is how many statements we have, 3. So 3 plus 2, 5 variables in SSA code. Okay, fine. I think it's the best example to understand SSA code. Yeah, we have very big expression here. The question is about, can you write the best 3 address code for this expression? Okay, and you always read the question carefully. Can you keep these constants directly in the expression, or do you need any additional variable for that? You decide based on the question. But if this question is given, then how do you perform, or how do you write the 3 address code? Okay, so now here there are no kinds of optimization. Sometimes when you see, like, you know, a plus b minus a, you know, plus c, something like that, when you see it, this a and this a you can cancel it, and actually b plus c only you need to perform. But there are no such things to optimize, right? There are no such things to optimize. So look at here, when they ask write 3 address code for this, write for b plus c, don't write for this a minus a, because they can be cancelled. So you can do some kind of optimizations to write the best 3 address code. Okay, I believe that you understood how to optimize this code, but here no such optimizations allowed. Now you should know how to write the sequence. You know, addition, multiplication, division, that's all you have, the 3 instructions, and multiplication, division have the same precedence, they follow left right, just do the same. Here we have division, we have here multiplication, then division. Okay, so we do that sequence. Then after that, okay, let me write here in the parenthesis to understand. Okay, r by 3, so we do this first, and t multiply with 5. We can do these two are independent, so any order is fine if you can save the space, and u multiply with v. So this has to be done first. All the 3 are independent, the order does not matter. Do first, but according to C language you do this one as consider as the first, but to optimize all the 3 are independent. Whether you do this first or this first or this first will not impact the result. Okay, this order will not impact the result because all the 3 are highest. You may require to perform left right, but when they are immediate, remember, they are not immediate, they are independent positions, so you can do in any order. So now you always focus on, can I reduce the number of variables? If I perform r divided with 3, r variable is free. When you multiply t with 5, t variable is free. When you multiply u and v, look at in the future, is there any u we use? No. So u and v are free. In case if that are not free, please don't perform. So when you perform any operation, that variable should be free. If not free in all of them, then you can do any of these operations. Okay, I am doing, you know, as per the order. R, this one I am going to do r divided with 3, I will put in r. So I am going to put in r. So I will write here r divided with 3, I will put in r. So I have a result, this one is r. Now t multiply with 5, I will put in t only, so that I don't have any difficulty to remember. And u multiply with v, so I will put in u, so that I don't need any additional space. Okay, we got the result, RTU. Then next you need to perform the division. So along with this you have a division, right? So you are going to divide with w. So you can put again in u if you want it. Okay, I am just putting it, u divided with w, put in u. So we have the result. Now all the multiplication and divisions are done. Next, addition, multiplication, addition, subtraction. So now we have many additions and one subtraction. So 1, 2, 3, 4, total 4 operations are there. Among them 3 additions and 1 subtraction. So now we have here q plus, another one plus s minus, then plus, whatever you have here, right? This one is done already. Now focus only on this, q plus r plus s minus something, t. This is a t, right? Now I am just assuming now you have 2 plus. Of course any plus can be done, but when you get a minus, before that plus should be done, because plus is coming first before minus. Then after minus, this plus should be done. So don't assume this plus will be done first. No, first this plus, so here any pluses does not matter because they will not change the result, but this minus should be done after this 2 plus, and this plus should be done after this minus. So if you do that, let me do in the same order. Q plus R, what is the result? Q plus R. I'm going to perform that. Did I complete this? Yes. Q plus R. Now after this, is that Q and R both are free? Both are free, so you can keep anywhere. Let me keep in Q. So I'm keeping in Q. Next, S I have to do. This Q plus S. Now after this, S is free. Q will be also free. So Q plus S. I can keep in Q. Now we have Q. Next, Q minus T. Q minus T. Q minus T. Where do you keep? Either in Q or T because both are free. So I'll put in Q better. Okay. And this much is done. Now Q plus U. U is this side result, right? Q plus U. Q plus U. Put anywhere. I'll put again in Q. That's fine. Now this is called as 3 address code. Now the question is, how many minimum number of variables required? First, how many variables we have here? But always read the instructions carefully. If you can't write 3 and 5 within the instruction, you must store at some address. For that you require additional address. First you store 3 and perform this so that that location will be free, and you can move that 5 into there and you can use that location. So be careful. Additionally, 1 extra needed if you can't put the 3 and 5 as a part of the instruction. But there are no such restrictions here, so let me do it. Fine. Now how many variables we have? You can see R. I'll just write how many variables we have. I'm just writing here. R. What else? T, U, V, W. Don't repeat any. Q. R already covered. S. T is covered, and then that is what is it? U. The last one. This is U. It's not 4. It is U. Okay. Fine. So how many variables? 1, 2, 3, 4, 5, 6, 7. Total 7 variables needed. 7 variables needed. Remember, 7 variables. In case if this 3 and 5 are not allowed to use as a part of the instruction, it will become 8. It will become 8. 7 will become 8. So here 7 variables required. 7 variables required. I'm trying to reuse the variables because I don't want to spend extra, I don't want to take or consider extra space while calculating. Okay. In case if you are going to do better than this, please let me know in the comment so that we can correct it. But this is how we do in calculations. But sometimes reordering is very important. If I'm not able to reorder properly, and if you are getting more additional addresses, you should be very careful. Okay, sometimes we get that situation. I'll help you. Okay, now what is the minimum number of variables? Now you got already answer, right? So for that I'll just take from here 1, 2, 3, 4, 5, 6, 7. 7 variables. How many instructions we have? 1, 2, 3, 4, 5, 6, 7, 8. Total here 8 instructions and 7 variables. 7 plus 8. How much? 7 variables already we have here. 1, 2, 3, 4, 5, 6, 7. 7 variables we have, plus the instructions that we have seen is 8. 8 instructions, 8 statements in 3 address code, best 3 address code, that too. So we can conclude that it will be 15 variables in SSA code. This is also in 3 address code, remember. Variables in SSA code. You can always use this concept to answer the minimum number of variables in SSA code. No need to write again 3 address code and SSA code later, right? So this can be done very quickly without wasting the time. Okay, this is one of the best question if you really want to practice. Now this is going to use the knowledge of the 3-dimensional array. How do you represent and then this is the 3 address code for the 3D array. And then the question is about when you declare a particular variable in high level programming language, how the 3 address code is going to be converted. So here it's already given, only you need to identify which of the following is the correct C programming declaration for this 3 address code. Okay, that is why you need to convert this high level, this 3 address code. This is what 3 address code. First read the question from first to last. For a C program accessing 𝐿𝐴𝐵𝐾, somebody want to access 𝐼𝐽𝐾, but they are declaring something else here. Declaration is different, accessing is different. These declarations will give you some indication, like you have 32 2Ds, 32 1Ds, 8 elements in each 1D, right? Here similarly you have 4 tables, 10, 24 rows, and each row you have 32 elements. So everybody has a different notation, and some are integer elements, some are character elements. You can see char. So everything is mentioned. Integer is 32 bits, means it is 4 bytes. Character is 8 bits, means 1 byte, right? It's a 1 byte. It is 4 bytes. And somebody want to access this 𝐼𝐽𝐾, for that this 3 address code is given to you to access 𝐼𝐽𝐾. And what else? Intermediate code is generated by the compiler. That's it. Now you need to find the declaration. Somebody declared and somebody accessing it. Now once it is declared, is this correct 3 address code to access this? To understand it, you should know exactly what is the integer size and character size. Both are given. So everything is given. You should know how to understand which declaration is right, which declaration is right. For that, first you should know what is this expression. Somebody want to access x of 𝐼𝐽𝐾. It means it's expression, right? They have converted into this form. This is I level, right? Now for this, compiler converted into some intermediate code form, some intermediate code. So this one is actually one expression, but it's broken into many statements in 3 address code. If you want to understand this exactly, just scan, that's it, bottom to top. Then you will get back to a simple expression to understand what happened. Let me help you here. So T5 is equal to x of T4. Okay, I'll just write somewhere, I'll come back here, right? T5 is equal to x of T4. So I'm just starting from here. Okay, x of T4. What is T4? T3 plus T2. You have to put here. Okay, x of T3 plus T2. What is T3? T1 plus T0. That you have to put here. And what is T2? That's k multiplied with 4. You have to put here. And what is T1? J multiplied with 32. That you have to put here. And what is T0? I multiplied with 1024. That you have to put here. And what is k is just accessing that index 𝐼𝐽𝐾. You can't substitute further. So T1, T0, T3, T2, T4 has to be substituted to see everything in 𝐼𝐽𝐾. So you need to understand how to substitute it. So I'm just doing it, but at the end I'll write only one expression. Remember, T5 is equal to x of T4. X of T4. And what is T4? T4 is T3 plus T2. T3 plus T2. What is the T3 plus T2? T3 is what? T1 plus T0. T1 plus T0. Put that. What is T2? T2 is nothing but k multiplied with 4. I'm just doing in a single scan most of the things. Now T1, what is T1? J multiplied with 32. J multiplied with 32. I did that. J multiplied with 32. What is T0? I multiply with 1024. Looks very big, but without this could take much time. Okay. K multiply with 4. Is that everything converted into 𝐼𝐽𝐾 now? If not, you should worry about it. So this is the expression equivalent to this one, but they have broken into multiple 3 address code statements. This 𝐼𝐽𝐾 looks like high level. It's high level. When you convert it, the addresses are considered to calculate. But anyhow, let me put it in the same sequence, 𝐿𝐽𝑘 in the same sequence here. So now I'm just converting back. So everything I'm deleting here. Now I'll just write the statement first. This is the final statement, right? X. What is the equivalent statement? X of, let me put it I first. This is I multiply with 1024. This is the first calculation, plus what is the J? J multiply with 32 plus K multiply with 4. Okay. Now this is the equivalent, the 3 address code, but it's expression now. Here you see, when you convert any 3 address or 3D array element into 3 address code, then actually you directly access the K. If you remember the row major and column major order, here only we take K to jump to that corresponding element in the row or column. Now here K multiply with 4. Why this 4 is given? Because each element size is 4. That 4 is considered integer size. So when you take the 4 out of this, what happens is X, because it's a 4 multiplied, because you are accessing the integer element. So to move to the proper addresses, this 4 is multiplied everywhere. So if you if you divide with 4, what happens? I'm just taking the common, that 4, okay? That 4 multiply with, because 4 we do not need it later. Now I'm just writing here I common, right? For it's common for all. So here I multiply with, so divide with 4 now, it will become 256. Just check it. 256, 2 power 8 and 2 square, it will become 2 power 10. And plus, here divide with 4, J multiply with 8 plus K. So this is actual way to access the element in 3D array. So now I is going to be multiplied with size of 2D, J is multiplied with size of 1D. So if you know how to represent 3D, this 256 basically size of 2D. So if you look at this 2, right, this represents size of 2D. This represents size of 2D. Last two. First one ignore it. The last 2. If you look at this, 32 multiply with 8, it's exactly 256. And 1024 multiply with 32, it's not 256. And 32 multiply with 8, it's 256, but you have taken 4 common, you are considering integer. If you want to consider character, definitely this is not 256, it's 1024 multiply with 32, right? So that's the problem. Here 16 into 2, 16 multiply with 2 is going to be 32. Anyhow, if you look at this one, is enough, that is clearly matching with option A. That's enough. 256 is nothing but, I can represent this, 256 is nothing but 32 multiply with 8. And the 8 is this nothing but size of 2D. This is the size of 2D. And this is the size of 1D. Exactly you have this 8 matches here. And this 32 multiply with 8 matches with this one. Anyhow, this 32 we don't consider because a number of tables, it is nothing but. But this is the size of each table, each 2D, and the size of each 1D. And the 4 represents size of the element integer here. This represents integer. So that's why we choose option A. Of course, it takes a lot of time to understand. Without having the knowledge of how 3D array represented in row major order or column major order, this question would be difficult. Is it right? So it's very important. It is C. So C follows row major order. C follows row major order. And straightforward given, just you should know, okay, this should be converted into expression so that you can easily understand. And here plus K should be there. It's not K multiply with 4. So that means 4 should be taken common. The 4 is a size of an integer. That is another hint. What is this 4? Is the size of integer. So either option A or option B, because option C, D are representing characters, right? Now once you got the 4, and this is enough to understand which is the option is correct. If this is matching by both of them, then anyhow 8 will decide the answer. Okay. So option A is the right. Now which of the following is our a machine independent codes. You know, right? C code is the machine independent code. Assembly code, no, machine dependent, because you deal with the registers and addresses. Intermediate code, machine independent. Machine code is machine dependent. Okay, this A and C are the right options for this question. Machine independent codes. Okay, we have some questions to understand, you know, how these various representations are used, and find the number of nodes and edges in the DAG. Now, when you have provided with this, you know, now there are 4 additions, right? You can't say A plus A only calculated. If you do A plus A you do once, another time you do A plus A, but you can't do now another A with A plus A. So that has to be done additionally. See that A plus A you can save the time. These 2 places you can use the same A plus A, but this A has to be used separately. So how to do that? Okay. Now I am trying to construct the DAG A plus A. A plus A. See that left and right. You don't take 2 spaces here. Remember, A plus A, don't construct this way. It will explain us 2 different addresses, 2 different nodes. In syntax you may do it, but not DAG. DAG you can't take 2 different spaces, 2 different nodes. It should be the same node. So here you take same node or same address. A plus A. Now I can use the same calculation both the places. So I do this plus. This calculation is nothing but A plus A. I can use left, I can use right. So we got this result now here, and plus A. So plus I will put here, and left is this one, and right is A. So this A I can take here. So this is going to be the best DAG for this expression. Okay, for this expression. How many nodes? 4 nodes. How many edges? 6 edges. Okay, 4 nodes and 6 edges. Similarly, you can just try for the 3 address code how many minimum variables required. So in the summary, if you have intermediate code, of course there are 3 address code representations I will describe here. In intermediate code you have linear form, non-linear form. In linear form you have the postfix, we have seen it, and we have 3 address code. Even we have 4 address code, but not required here. 2 address code, 4 address code, and so many are there. And we have SSA code. This 3 address code further you can use to represent efficiently. You may use to represent different ways using data structures. You can write triple notation to save the space, quadruple notations, or you may use indirect triple notation. Further you can use various ways. Example, you have x is equal to a plus b. What do you do in triple notation? In triple notation, x is equal to a plus b. You will be having address, let's say 1000. At 1000 you will be having 3 columns only, like a, b for operands, or I can say first you may use, order doesn't matter, plus operator you may use first, or operands. So plus I used first, that a, b, that order is very important, a and b. So I can say headings. This is operator, this is operand 1, another one operand 2. Just like plus a, b. Assignment is not required. Whenever you want x, you should come to 1000 and you should calculate. If I am going to use x next, let's say I am using c multiply with x, let's say I am storing in y. What you have to do next, let's say at 1010 you have multiplication. C with x you have to do, but x I don't have, so I will go to 1000, I will use it here. You will mention the address here. This is how you write the triple notation. But in quadruple it is straightforward. You are going to use all including result. So if you want to use quadruple, that will become so easy. Like the same instruction, a plus b. Now you have, let's say 1000 address you will be having. So you have operator, operand 1, operand 2, like left operand, right operand, and result. So how do you store now? The operand 1 is a and operand 2 is b, plus is operator a, b. Result, where do you store? Some address x. Now you don't need to remember the 1000, x is fine. Next, c multiply with x. So multiplication, let's say this is 1000, let's say 20, and multiplication c with x you can write now. You don't write 1000 because I have the x to have the result of a plus b. Now you store in y, so you keep in y. So this is the advantage of quadruple. Here no need to calculate. Whenever you need addition, already is calculated and stored in x. But what is the disadvantage of quadruple? It takes a lot of space. But if you are reusing that calculation again and again, the quadruple already has a result, so it can perform quickly. But here if I want to use a plus b 100 times, then 100 times you should come to this 1000 address, you should calculate it. So that takes some time, but space is advantage compared to quadruple. Indirect triple means instead of storing this, instead of giving 1000, right, you give indirect address of 1000 here, so that you can save, you no need to deal with a plus b address directly. So let's keep here 2000. At 2000 you have the 1000. So you are giving indirect addresses. That's all the difference. But indirect triple is almost same as triple, but instead of giving 1000 you give some other address, and there you will have actual instruction. Okay, this is what you have in this 3 address code. In a non-linear you have what you have: syntax tree, DAG, and there is another one we'll be discussing in CFG, control flow graph. We'll be discussing in code optimization. Okay, this is all about intermediate code and very easy topic. Practice that, finding the number of variables, minimum number of variables in 3 address code and SSA code. Also finding number of nodes and edges in DAG. Okay, remaining topic like control flow graph we'll be seeing in coming lecture. Yeah, thank you so much for watching this video. See you in the next lecture. Bye bye, take care.